This presentation is entitled Production Decline Analysis for Unconventional Reservoirs Using Fekete Software. And in this presentation, I'm going to talk about how we use Fekete Harmony, specifically the F.A.S.T RTA module within, to analyze unconventional production data sets. I'm going to start by doing a little bit of an overview. And in the overview, we'll talk about the commonly used approach for analyzing production data of unconventional reservoirs right now, as is standard in the industry. And then we'll talk a little bit about what we call our Fekete approach or simplified approach, and talk about some of the advantages of using this new approach for unconventional reservoirs. And then I'll get a little bit into the theory behind the physics of fluid flow in unconventional reservoirs and how we can analyze that and get a better understanding of those reservoirs using the Fekete Harmony software. The commonly used approach in the industry right now is to use a modified hyperbolic decline curve. And the hyperbolic exponent is typically chosen by a best fit of the data, which could be a nonlinear regression fit of the data. In addition, there's a limiting decline rate that's chosen, usually based on an assumption or an analog field or well. Some of the problems that are associated with this approach, I think, are well known to many of us that are petroleum engineers in the industry. For one, the b-value or the hyperbolic exponent is very sensitive to data. For example, if I add another month's worth of production data to the end of my history, it can drastically change the b-value. So it's usually not a good idea to use the hyperbolic exponent or the b-value as a history matching parameter. This can cause lots of problems and inconsistencies in our analysis. Yet this is something that's done on a daily basis with a lot of companies. The limiting decline rate is another thing. It's a property at which, limiting decline rate where we switch over from a high hyperbolic to a low hyperbolic or exponential decline. And the problem is it has no physical meaning. We can choose it using an analog, but very often that number is just plucked from thin air, so to speak, and there's no physical meaning behind it. The problem with conventional decline curve analysis is it fails to address the uncertainty. In conventional reservoirs, usually we have a pretty good idea of what the P90 and P50 reserves are. In unconventional reservoirs, P50 reserves are often very uncertain, especially early in the life of the well, and this is due to long-term transients in the production. They go on for a long time, and the conventional decline curve approach fails to address our lack of knowledge about where that EUR is really headed for. And then finally, kind of to wrap this up, because every company and even every play within each individual company is analyzed differently, and we're using different assumptions for decline curve analysis, there is really no apples to apples comparison industry-wide using the state-of-the-art or the standard approach in the industry right now for reserves. And this presents a big problem because we can't come up with a consistent appraisal of these resources. What I'd like to propose instead is our approach. And it's very similar to the conventional decline curve approach. We don't really want to differ too much from using standard decline curves. However, we're going to use them in a different way. To start out with, we're going to use diagnostic plots that we've spent many years using in RTA and have proven their worth over the years to identify flow regimes. And then we're going to use the modified decline curves, but specifically using b-values and decline rates that are consistent with the physics of the problem. So we can relate it back to the science of the fluid flow rather than picking arbitrary or assumed values. And then finally generate multiple forecasts instead of just a single forecast to capture the uncertainty in the EUR. The benefits of an approach like this is that it's just as quick and simple as standard decline curve analysis, but we gain much more knowledge about the reservoir because we're assessing the fluid flow regimes in the reservoir and getting a qualitative understanding of what's going on, as well as just an estimate of expected ultimate recovery. In addition, we get a consistent and reliable determination of decline curve characteristics. I don't think the importance of that can be understated. We can now, with this approach, have a systematic comparison between production profiles from wells within a play and across multiple plays that is robust. We can clearly identify where the uncertainties are. And this whole approach is going to be defendable to reserves auditors, which I think is of tremendous importance to operating companies of these resources. The areas of applicability of the approach that we're going to talk about that we can apply in Fekete Harmony software is basically anything that's tight, low permeability, and fractured. So conventional plays, gas and oil, both vertical and horizontal wells that are fractured. So single fracture stage vertical wells or multi-stage horizontal fractures, and also shale gas. So shale plays that are vertical fractured or horizontal fractured. Any of these types of plays we can apply this technology to.